Alrighty, so in this video I'm going to take a look at the paper 2 specimen paper, the first set of specimen papers from the full A-level paper. So this is essentially looking at stuff that you would typically look at in year 13. So let's have a look at question 1. So we've got a system for separating two minerals and we're doing it using an electric field. So you can see here you've got the electric field applied across these two locations, so applied horizontally, and we've got it falling a distance of 4.5 meters there. So we're going to apply some friction to charge up the grains. I'm going to charge them in oppositely, so they travel opposite directions in the electric field, and we've got them separated by 0.35, and like I said earlier, they fall 4.5 meters. Assuming the velocity of the particle was 0 when it leaves the hopper and it enters the regions between the plates, calculate the time taken to fall between the plates. So because the electric field is applied horizontally, we don't have to consider that for the vertical motion. So what we're going to do is we can use a Suvat equation, because effectively it's in free fall in its vertical direction anyway. So we can use S equals ut plus half a t squared and then u is 0, so we can cancel that out. And we want time, so we're going to rearrange to make time the subject. So we'll take the 2 across to the other side, divided by the acceleration due to gravity, which is so that's the acceleration. So it's going to be 2 times by 4.5, which was displacement. I'm going to define downwards as positive, so we're going to use just positive numbers. You could have done this with negative numbers, but you get the same thing. So that's the calculation we're going to do, and if we do it, the time comes out as 0.96 seconds to fall the total distance there. Okay. So if we've got a potential difference of 65 kilovolts applied between the plates, show that the particle of specific charge 1.2 times 10 to the minus 6 coulombs per kilogram has horizontal acceleration of about 0.2 meters per second. So we can calculate the field strength of our uniform electric field by dividing the potential difference by the separation. So that's a potential difference of 65,000 because it's in kilovolts, and the distance was 0.35. So then let's get out the old calculator. Let's see what's that. 65,000 and 0.35, and it comes out. It's quite 185,714.2. Blah 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 blah. Doesn't matter too much. We'll keep that number. Okay, so that's the field strength. What we want is the acceleration. So first we're going to calculate what the force is. So force is field strength times by the charge, and acceleration is the resultant force divided by the mass. So that's the field strength times by Q over M. Q over M being the specific charge. So we've got the field strength, so we times it by the specific charge, and it comes out as 0.22220. So what we did there, so we took our answer to this part, times by 10 to the 1, 2, 3, 4, 5. 10 to the 5 times by a specific charge times 10 to the minus 6. I'm showing my working here because this is a show that question, so you should show every stage that you're doing. And let's give the unrounded answer first, so it comes out as 0.2228, which is approximately 0.22 meters per second squared, which is what we were looking for there. Okay. Calculate the total horizontal deflection of the particle that occurs when falling between the plates. So we know its initial motion in the horizontal direction is 0 because it's falling vertically initially. So we know the u is 0. We don't know what its final velocity is. We don't know what its displacement is. We just calculated its acceleration, so that was 0.22 blah blah blah, and we calculated the time earlier, it was 0.96 blah blah blah. So what we're going to use is the same equation we did before. So we can use S equals ut, but u is 0, so we can just do half a t squared. So we've got a times by 0.96 squared divided by 2 comes out as 0.1026 blah blah blah. So that's going to be 0.10 meters. There would be your deflection there. Explain why the time to fall vertically between the plates is independent of the mass of the particle. So the first point I make is that in the vertical direction, the only force acting on the particle is the weight force equal to mg. But we want the acceleration, so acceleration is force divided by the mass. So if the weight force is the only force, that is going to be equal to g. And as we had before, the time is calculated by doing 2 times the displacement divided by the acceleration. So as mass is nowhere in this equation, we can see the time is independent of mass. Okay, so that's what we've got there. Okay, so let's move on to the next part. So then it wants us to explain why the horizontal acceleration of each particle is different. So what the first thing is they told us in the question was that the charge is different. So if your charge is different, we saw that the acceleration is a function of the field strength, charge, and the mass. So those are the things that can affect it. So let's do that to start with. So we saw that the acceleration of an object, let's actually make that look like an A, was calculated by doing field strength times charge divided by mass. So field strength stayed the same the whole time because we've got the same potential difference. So the two things that could affect the acceleration are the charge or the mass, because the field strength stays the same. So if we alter either of those two things, we're going to end up changing the horizontal acceleration of the particle. Alright, and so that's what we've got there, explaining the factors that could affect it. Okay, so that finishes question 1. Let's move on to question 2. Alright, so in this question we're going to be looking at some capacitors, so continuing looking at uniform electric fields. So we've got plates of an area 250 centimeters squared, and we've got a relative permittivity of 2.3 for the dielectric between the plates. Calculate the thickness of the polyethylene sheet. So we've got an equation for relating these two things. So this is your equation to calculate capacitance. So we want the thickness of the sheet, effectively what we want the plate separation. So what we're going to do is the area times the various permittivities and divide that by the capacitance. So we want 250, but that's in centimeters squared, so we're going to times it by 10 to the minus 4 to turn it into meters squared. We've got the permittivity of free space, so 8.85 times 10 to the minus 12, times the relative permittivity, so we've got 2.3, and we divide it by the whole capacitance, so 370. It says picofarads, which is times 10 to the minus 12, So if we get out the old calculator and type that in, we end up with a value of 1.4 times 10 to the minus 3 meters, or 1.4 millimeters separation effectively. Okay, so that's that one. So the capacitor is charged, so there's now a potential difference of 35 volts between the plates. The charge on the capacitor is then 13 nanocoulombs, and the energy stored is 0.23 microjoules. The supply is now disconnected, and the polyethylene sheet is pulled out from between the plates without discharging or altering the separation of the plates. Show that the potential difference between the plates increases to about 80 volts. So, if you disconnect the supply, that means the charge stays the same on your plates. So we know potential difference is going to be the charge divided by the capacitance. And what we're essentially saying is charge stays the same because it's disconnected. Capacitance, as we've just seen, is calculated like this. So what is just said is the separation stays the same. We haven't changed the area of the plates, and obviously we haven't changed the permittivity of free space. What's happened is this number is now 1. So the capacitance has been effectively divided by 2.3. So if the capacitance has been divided by 2.3, that basically means this whole expression up the top here is going to be multiplied by 2.3. So the final potential difference is going to be 2.3 times whatever the old potential difference was, 35, which comes out as 80.5, which is around 80 volts there. So that's what happens there. We could have done this by calculating the new capacitance and then doing charge divided by that, but this is fairly straightforward to see what's going to happen there. Okay. So it says calculate the energy that's now stored by the capacitor. So we said the charge stays the same, but the potential difference is now increased. So we've got the potential difference is 80.5. We had the charge stored on it, I think it was 13 nanocoulombs, so 13 times 10 to the minus 9, times by the unrounded answer, so 80.5. And if we calculate that, so 13 times 10 to the minus 9 times by 80.5 divided by 2 comes out to 5.22 times by 10 to the minus 7 joules, or 0.52 microjoules there. So that's what it wants the answer in, so let's do 0.52 microjoules. Explain why there is an increase in energy stored by the capacitor when the polyurethane sheet is pulled out from between the plates. So when you have a dielectric between two plates, the dielectric molecules align with the field. So you get the positive parts of your dielectric aligned with the negative plate and vice versa. So essentially your dielectric is attracted to your plates. So if you're going to take it out, you have to do work against that attractive force, and that work you put in is why we get an increase in stored energy. So let's get that down. So that's the first part there. So the dielectric molecules align with the field, so their positive end is towards the negative plate. So actually the dielectric becomes attracted to the capacitor. And so we finish it off. We have to do work to remove it because it's attracted to the capacitor. That work is then transferred to energy stored in the capacitor, which is why it increases. Okay, so that finishes question 2. Let's move on to question 3. So we're going to look at the motion of gas. So it says state 2 assumptions made about the motion of the molecules in a gas in the derivation of the kinetic theory of gases. So there are many assumptions made. So we assume the molecules move randomly. We assume the collisions are all elastic. We assume the collision time is negligible compared to the time taken between the collisions, and that we assume the molecules travel in straight lines as well. So there's loads of stuff we can put down, so let's get that there. So what the motion of the molecules is random. The molecules travel in straight lines. Travel in straight lines. The collisions are all elastics. And the collisions take negligible time. And that's compared specifically compared to the time between collisions. Okay, so those are the assumptions made in terms of the kinetic theory model. These are things you should be familiar with from going through that process. So it says, use the kinetic theory of gases to explain why the pressure inside a football increases when the temperature of the air inside it increases. Assume the volume of the ball remains constant. Okay, so if we're keeping the volume of the ball the same, that means the area that the force from the gas molecule is spread over is pretty much the same the whole time. So that's not the reason for it. But if we increase the temperature, what you should know is the kinetic energy of the gas particles, or the mean square speed, increases. So that's going to decrease the time between the collisions, and it's also going to increase the change in momentum from each collision. So from that, a greater force and therefore a greater pressure is experienced. So let's put that down. Okay, so that's what we've got so far. So we've got the same area, but the time between collisions and the change in momentum increases. So you should know that using Newton's second law, force is the rate of change of momentum. So we get the change in momentum increases because it's an elastic collision. If it started with more momentum, it's going to end up with more momentum in the opposite direction, so there's a bigger change. And the time decreases, both of which act to increase the force. And then pressure is force divided by area. So I said earlier that the area stays constant. So your area is staying the same, your force is increasing, so your pressure is going to increase there. So let's put that into words. Okay, so that then rounds off this part of the question. Okay, so let's move on to the next part. So the laws of football require the ball to have a circumference between 680 and 700 millimeters, and the pressure of the ball is required to be between these two values. Deflate gate alert, something or other. So a ball is inflated when the atmospheric pressure is 1 times 10 to the 5 and the temperature is 17 degrees. When inflated, the mass of the air inside the ball is 11.4 grams and the circumference of the ball is 690 millimeters. Assuming the air behaves as an ideal gas and the thickness of the material used for the ball is negligible, deduce if the inflated ball satisfies the law of football about the pressure. And then we've got the molar mass of air. So first off, let's work out how many moles of air we've got. So we're going to do mass divided by molar mass. So let's calculate that. So we've got 11.4 divided by 29. And that comes out as 0.393, blah, blah, blah. So that's how many moles of gas we've got. But we can also work out the original radius of the ball. So we've got the circumference, so if we divide by 2 pi. That would give us the radius of the ball. So let's do that. 690 divided by 2 divided by pi gives you 109 millimeters, or 0.109 blah 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 meters there. And what I just put in 1,000 there to convert into meters. Okay. So having worked out the radius of the ball, we can work out the volume of the ball using 4/3 pi r cubed. So let's do that now. So let's cube our radius times by 4 divided by 3 times by pi gives you a total volume of 5.5 yada 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 times 10 to the minus 3 meters cubed. So now we can get our pressure, which we're going to calculate using nRT over V. So the number of moles we've already got, so it's 393. The gas constant's in your formula sheet, 6.31. The temperature in Kelvin is 290 because it's 273 plus 17. We're going to divide all of that by 5.5 times 10 to the minus 3. So let's do that. So 0.393 times 8.31 times 290, all divided by my answer. That comes out as 1.7 times 10 to the 5. And we need the pressure above atmospheric pressure. So effectively it's above by, we have to take away 1 times 10 to the 5 from that, by that answer. So it's above by 0.7 times 10 to the 5 pascals. So let's have a look at our criteria. So it says it has to be between 0.6 and 1.1 times 10 to the 5 above atmospheric pressure. So it is in that range. So essentially what that means is it is an appropriate value. So that would be our conclusion there. So so this is inside the acceptable range, is your final conclusion there. Okay, so that finishes that part and finishes question 3. Let's move on to the next part. Okay, so an ancient sealed flask contains a liquid assumed to be water. An archaeologist asked a scientist to determine the volume of the liquid in the flask without opening the flask. The scientist decides to use a radioactive isotope of sodium that decays with half-life of 14.8 hours. She first mixes the compound with this much sodium-24 with 1500 centimeters cubed of water, and then she injects 15 centimeters cubed of solution into the actual flask itself. Show that we've got 7.5 times 10 to the 10 atoms of sodium injected. So first of all, we can work out how many grams are injected. So grams injected, so there's 3 times 10 to the minus 10 grams in 1500. So in 15, there's going to be that divided by 100. So there's going to be 3.0 times 10 to the minus 12 grams in there. So now we can get the number of moles by dividing that by the atomic mass, which is clearly 24 grams per mole. So let's do that. So 3 times 10 to the minus 12 divided by 24 gives you 1.25 times 10 to the minus 13 moles. But we want atoms, so we need to get this number multiplied by Avogadro's number. which is essentially times that by 6.02 times 10 to the power of 23, and we get 7.525 times by 10 to the 10, which we can see is roughly 7.5 times 10 to the 10 atoms. So that has worked out. Okay. Show that the initial activity of the solution that is injected is about 1 times 10 to the 6 back. So we can get the decay constant is going to be the natural logarithm of 2 divided by the half-life. So that was 14.8 hours. It wants in becquerels, which is per second. So let's convert hours to minutes to seconds. So let's do that value. So then 2 divided by 14.8 divided by 60 divided by 60 gives us a decay constant of 1.3 blah 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 times 10 to the minus 5, and that's in s to the minus 1. An activity you can calculate using your decay constant times the initial number of atoms, so that answer times by 7.525 times 10 to the 10 is 9.78 blah 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 times by 10 to the 5 becquerels, which is roughly 1 times 10 to the 6 if you round it to one significant figure. So that's got what we were looking for there. Okay, so let's move on to the next part. She waits for 3.5 hours to allow the solution to mix thoroughly and then extracts a 15 centimeters cubed sample from the flask and measures its activity and finds it to be 36,000 becquerels. Calculate the total activity of sodium after 3.5 hours and thus determine the volume of the flask. So activity follows an exponential relationship like this. So we know what the initial activity was. It was 9.78 blah 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 times by 10 to the minus 12. We know the decay constant in 1 over hours is that, so we can times it by 3.5, giving us a final activity of the sodium of times by the exponential of 2 divided by 14.8, 3.5. And that comes out at a value of 8.3 times 10 to the 5 becquerel. So that is the activity of the sodium after 3.5 hours. So essentially, we didn't get that value, we got this, so essentially we know that the sample is only a small fraction of this one. So if we do the ratio of those activities, that would tell us the ratio of the two volumes. So let's do that. So the original volume is going to be 8.3 blah 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 times 10 to the 5. That's how much we expect the activity to be. This is how much it should have been. So that gives us an idea of the ratio between those. And then we put 15 milliliters of the sodium in to start with So this will tell us what the total volume of the flask is now. Which is 3, 4, 6, 2, blah, blah, blah. So that is the total volume. So then the volume of the liquid originally would be that minus 15, because we stuck an extra 15 in. So that's going to be 3.4 times 10 to the 3 centimeters cubed there, to SF there, because we need to subtract 15 from it. Okay, so that finishes that part. And the next part says the archaeologists attained an estimate of the volume, knowing that similar empty flasks have an average mass of 1.5 kilograms and the mass of the flask in the liquid was 5.2. Compare the estimate that the archaeologists could obtain from these masses with the volume contained in 4.3 and account for any difference. So what we're going to do is calculate the volume using this. So we want volume, it's going to be the mass divided by the density, so that's going to be 5.2 minus 1.5 divided by the density, so 5.2 minus 1.5 divided by 1,000 gives you the volume in meters cubed. So we're going to times that by 1,000,000 to turn that into centimeters cubed. So that was 3.7 times 10 to the minus 3 meters cubed, or 3,700 centimeters cubed. So quite close, but a larger value. So then it wants us to account for any difference. So why do we get a difference? Well, the whole time we've been assuming the liquid is water, but if it isn't, that would make a difference to this calculation at the bottom but not the one at the top, so that might account for any difference between them. So let's put that down. This method assumes the liquid is all water, which it might not be. We have no idea what the ancients may have put into their flasks, but our best guess is that it's water. Okay, so that finishes question 4. Let's have a look at question 5. Okay, so we've got the setup for investigating induction. So this is the search coil experiment. When the switch is closed, there is a current in the coil in circuit X. The current is in a clockwise direction as viewed from position P. So that means this here, hang on, is going to be the south pole, and on this side is like the north pole end. Explain how Lenz's law predicts the direction of the induced current when the switch is opened, and again when it is closed. Okay, so when you close the switch, the current is going to go from 0 to going round clockwise. So then the induced current will then therefore have to go anti-clockwise because it has to be in the opposite direction. So that's when you close the switch. When you open the switch, the current goes from going anti-clockwise to nothing, so the change is then opposite, so the current travels clockwise to oppose the decrease. So let's put those down. So that's what happens when we open the switch. The current in the first coil goes from going clockwise to 0. So the opposite thing happens to the current in the other one, so it goes from 0 to clockwise. Then if we look at when the switch is closed, Okay, so then that's what we've got when the switch is closed too. So again, the change is always opposite to what happens in the primary coil, if you want to call it that. Okay, so let's move on to 5.2. So we've got an earth inductor, which is a 500 turn coil, and we've got two diagrams showing how it's set up. So we've got it set up so its area is perpendicular to the field. Okay, so we've got a diameter so you can effectively work out the area, and it shows how the output changes with when the coil is rotated at 1.5 revolutions per second. Let's zoom out a little bit so we can see that. Okay, so what the question actually wants us to do is determine the flux density of the horizontal component of the Earth's magnetic field. So what we're going to essentially work for is we're going to look at the maximum EMF, which you should know is given by this equation here. So what we're going to need to do is work out what A is, what N is, and what omega is, and we're going to need to measure the EMF, the maximum, from the graph. So let's first rearrange this. So we want to get B, so we're going to need to do EMF divided by A, N, omega. So let's get those three things separately. So A is going to be pi d squared over 4. So we were given the diameter, which was 35 centimeters. So that's going to be pi times by 0.35. We need it in meters squared over 4. So let's calculate that now. So 0.35 squared times by pi divided by 4, and that gives us 0.096 blah, 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 meters squared. From the graph, the maximum EMF we can read off is 5.6 volts, and the angular speed is equal to 2 pi f. We were given f is 1.5, so we can do 2 times 1.5, so that's actually 3 pi. So what we can do now is calculate our field strength. So we had a total number of turns of 500, so let's multiply by the area by 500, times by 3, times by pi. And we do 5.6 divided by all of that, and that gives you a field strength of 0.012 Tesla there, which is the unit of field strength. So that's what you've got there. Okay, so then question 6 is got a passage to read, and then we're going to answer some questions. So this passage is about like different kinds of satellites by the looks of it. So I'm going to read through that silently, so you can read through it yourself as well. So the first thing it wants us to do is describe 2 essential features of the orbit for it to appear geostationary. So the first is it needs to orbit above the equator. And the other thing is it needs to be moving over the time period of 24 hours. And it needs to also be going around in the same direction as the Earth. So the Earth rotates around on its axis, so it needs to be going the same way. So it needs to travel it from west to east, effectively, as it looks down on the Earth. So those are your features there. So that's actually 3. We want to calculate the time taken in seconds for the satellite mentioned in line 7 of the passage to complete 1 orbit around the Earth. So we want the time period there. So time period is 2 pi over the angular speed, and you are given the angular speed, So that was 2 pi over 2.5 times 10 to the minus 4, giving us an overall time period of 2.5 times 10 to the 4 seconds. Alrighty, there. So that's our time period. Show that at a distance of 12,000 kilometers from the satellite, the beam has a width of 1900 kilometers. So, we know, because it tells us, we can calculate the angular width in terms of the wavelength and the distance. So we've got those two things, where d is the 1.7. So what we need to do is work out what the wavelength is, which we can do because we've got the speed of light and we've got the frequency. So let's do that first. We've got that, and we've got, it's 11,000, but it's in mega, so we need to turn it this, giving us a wavelength of 3 times 10 to the 8 divided by 11,000 times 10 to the power 6, which is 0.27 blah 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 meters. So that's gonna make the angular size 25. What am I doing? 27 blah blah blah. By the size of the dish, which is 1.7. So divide that by 1.7, giving you 0.16 radians and then you should know the length of an arc is given by r theta. So we know how far it is, so we know like what the r is. So we're going to times that by the angle. So times by 12,000, which comes out as 1925 blah 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 kilometers, which is roughly the 1900 that we were looking for there. Okay, so that's that one. So the satellite is in a polar orbit and passes directly over a stationary receiver at the South Pole. Show that the receiver can remain in contact with the satellite for no more than 20 minutes each orbit. Okay, so what I'm going to do is work out the speed of the point on the Earth. So we already know the angular speed, so we need to multiply radius of the Earth by the angular speed, which we already have, like this, and then that's times 10 to the minus 4. I will also need to times it by 1,000 to turn it into meters per second, because that distance is in kilometers. So let's do that. 6,400 times by 1,000, that's now in meters, times 2.5 times 10 to the minus 4, gives you the velocity of 1,600 meters per second. So that's how fast a point on the surface of the Earth is traveling. So now we've got the width we can work with. We're going to divide that by 1,600. So I'm just going to go back up and dig out the width was. It was 1925 blah blah blah. Give you a time of we need to multiply that by 1,000 because that was in kilometers, remember? So that gives you a time of 1,200 seconds. So divide that by 60, and that comes out as 20 minutes. Okay, so nice question there. Okay, so the same satellite is moved into a higher orbit. Discuss with reasons how this affects the signal strength and contact time for the receiver at the South Pole. So first of all, the signal strength is going to be weaker because it's got to travel faster, and because it's an electromagnetic wave, we know intensity follows an inverse square law with distance, so let's put that in. But if we move further away, if we think how we calculated the beam width earlier, we did the distance times by the angle. So the angle is going to stay pretty much the same, but if the radius increases, that means the beam width increases, so we can actually get a signal for longer. Alright, so that's what we've got there. So that completes the longer answer section of this paper. I have already done a video looking at the shorter multiple choice section if you want to check that out. If you've spotted any mistakes or there's anything that's not clear, please do comment on this video and let me know. But thank you very much for taking the time to watch this video.